Yeah.
Cool, go ahead.
Sure. Yeah. So I work at the Ethereum Foundation. I do a bunch of work on like things to do with privacy and things to do with scalability. It's really nice to meet you all and hear about your projects. I think there's like a couple of like maybe interesting collaborations that we could do. But let's maybe do that after the call, after the presentation. Let me go for the presentation first because I don't want to run out of time. Cool. So
one more note, Barry. So I have to run around in the background and do a few things to close up the Airbnbs out here. Can I hand you host privilege in case I have to hop early, so that way you have control over like pausing, starting, stopping the recording?
Sure, but I have no idea how to do that.
Okay. I think the main thing is just like if I end up having to drop, the recording will still continue until you leave the call if I make you host.
Okay, sounds good. I can do that.
Sweet.
Okay, cool. Yeah, so can you all see my screen?
Yep.
Okay, great.
Yes.
Yep.
Cool. So this presentation is about like PLONK and the next generation ZKPs, the kind of like the next step of like what we can build. At the moment, we're building mostly with Grout 16, and like as I think Tony mentioned, there are some optimizations that we can apply when we move to the next generation ZKPs. So I'm not sure this presentation is gonna go and talk a lot about PLONK at the start. And like the goal here is I'm gonna talk about polynomial commitments and how to open polynomial commitments. Then we're gonna make like a simple constraint or a couple of simple constraints. Then we'll talk about a simple prover. We'll talk about example applications and some like future work projects. And like just a disclaimer at the end, like this is supposed to be in spirit, this is correct, but I think that there's a lot of details that have been kind of left out. And I think that it's okay to leave out those details because those details end up being very similar to the kind of methods that we're applying here. It just complicates a lot the description and the understanding. So if you're interested in exploring the like deeper level, there's a whole bunch of posts like this. This one by Vitalik is a good place to get started. Anyway, this is I hope that this is like a nice place to get started, because I try and just keep it high level ish. But we're going to talk about pairings and we're going to talk about polynomial commitments, so we might go a little bit deeper. Like normally the way that my talks go is that like it starts off really slow and then it gets to the point where there's like a lot of information. And as soon as you get past the point where there's a lot of information, the rest of it is like relatively easy. There's tends to be, and maybe I should try and avoid this, there tends to be this point where everything gets really complicated, and then after that everything is super simple. But I don't think that it's going to get that complicated. I'm just like trying to mention this as like a semi-motivational thing, that like if things get like really difficult, it's only going to be really difficult for a short time. Also, if you don't get that kind of like key insight of the really difficult part, you can still gain a lot from the rest of the talk, from the pieces at the start and the pieces at the end. And I'll tell you when we get to the really difficult part. So if people want to like not pay attention for a while, or if you kind of know about this stuff a little bit, you can kind of chill out for a bit, and I'll warn you when you need to pay a little bit of attention. Okay, so let's go. So what is a polynomial? Oh yeah, the final thing is that like, please feel free to interrupt if you have questions. If you don't understand, please let me know. Just speak up in like you can leave something in the chat, but I don't know if I can see the chat if you leave a message or not. But if you, please feel free to interrupt, and happy to have any questions and happy to have like a conversation. And like if y'all think we want to go in another direction from the talk, that's okay too. I'm happy to just discuss whatever y'all are interested in. But let me start here, and like at some point y'all can just pull me away on some other stuff if you feel like it. Okay, cool. So let's talk about polynomial commitments. So what is a polynomial? A polynomial is just like x plus x squared plus, it's like some coefficient times x plus some coefficient times x squared plus some coefficient times x cubed plus some coefficient times x to the fourth. And this is one way to represent a polynomial in coefficient form. There's other ways to represent the polynomial. You can represent it by just having like a whole bunch of evaluations of that polynomial. So this is what a polynomial is. And like, basically we want to have a polynomial commitment, which is like something that sort of binds you to a, so a polynomial commitment is like a very short way of representing a very long polynomial. Like this polynomial has 4 terms, it's not really that long, but if we can find like a shorter way to represent really, really long polynomials, that's very helpful for us, because that means that we're able to do like a lot of polynomial checks very quickly. So how can we make a polynomial commitment? And the answer is that we can make a polynomial commitment by evaluating it at secret point. That we have some secret x, we set x equal to some secret, and we evaluate it there. And like this is, of course, like difficult to imagine. Like, how can you evaluate a polynomial at a point you don't know? We're going to talk about this in a minute. And the final thing that we want to do with our polynomial commitment, we want to commit to it, but we also want to open it. We want to say that, okay, given this evaluation of our polynomial at a secret point, we want to evaluate it at another point, or we want to make a proof that shows us the evaluation of that at another point. So this is a polynomial commitment, and this is what we're going to talk about for the next like couple of slides. And this is going to be this is still kind of easy stuff. We're going well. Don't need to pay attention. You can kind of chill out. It's all good. Okay, let me set some assumptions. Maybe you all are aware of this, maybe not. So first of all, we're going to be doing all our arithmetic in what's called a prime field. And a prime field is basically just a fancy word for everything is done modulo a prime number, right? So whenever you do some arithmetic, it's the result, you just do a modulo the prime field at the end. And I made a simple prime field here just to show us. So it's like 1 modulo 7 is 1, 8 modulo 7 is 1, 13 modulo 7 is 6. And like you can do like 1 plus 9 modulo 7. You can do all of this stuff, and we just apply the modulo at the end. So still easy stuff, modulo arithmetic. It's just like regular arithmetic, but we just forget some of the information. We just don't care about some of the extra bits of numbers. Right, in this field we have an elliptic curve. Yeah, an elliptic curve is basically just like something that we use for cryptography. It's like it's just like our other polynomial here. It's just like 2 terms instead of 1. And basically the elliptic curve is defined like this, where you have an x point and a y point, and then we have some constants a and b, and then for every x we can calculate a y, and this makes a curve that I should have put a picture of a curve here that just looks kind of cool. And basically you can use that points on that elliptic curve have some special properties, and we're going to use those special properties later to do some stuff that we want to do. These elliptic curves have something called a generator on them, and a generator is basically a point on the elliptic curve that, like, you take that point and you add 1 to it, you generate another point. You take that other point, you add 1 to it, you get generated another point. And a generator is a point that will just generate all of the points on the elliptic curve. So you have 1 point, and then you're able to get all of the other points by just adding 1 to like the previous one with this kind of algorithm. So we have a generator G1 and G2 on these like 2 separate elliptic curves. Cool. This curve is pairing friendly. And pairing friendly is basically, it's kind of like, we're going to get to this later. It's basically this kind of encrypted multiplication or bilinear map. Like a bilinear map means that like you have like something in G1 or you have something in G2, and you can map those to like the same point in GT, in this other kind of group. G1 and G2 are like are generators of a group. So you can map so basically what it does is, like, we have one thing in G1, we have one thing in G2, and we want to compare the 2 together. But we can't compare the 2 together because they're different things. It's like saying what's better, hats or dancing. You can't compare them because they're just completely different. You can't compare them because they're completely different, but like a kind of a pairing lets us kind of convert hats and dancing into this base unit that we're able to compare more easily.
Barry, real quick, there's a question in the chat. I think your audio is clipping. Can you lower your mic volume a little bit?
Yes. 1 second. Is it, yeah, okay. Input, okay. Mic volume. How is that? Is that better? Lower? Testing. Okay, how about that?
Yeah, I think that's a bit better. Yeah.
How about now? Is that good?
Yeah, I
Lower?
think it's a bit better.
Okay. Acceptable better? Okay, let's
Yep.
go.
Yes.
Okay, so basically we have this like pairing that lets us compare, the pairing lets us like change something so we compare two different things together. And then the final thing to remember is that like, oh, oops, sorry. The final thing to remember is that like, if we have something that's like a generator multiplied by the secret, and we end up with X, if we have X and G1, it's impossible to calculate our secret. It's kind of like encrypting the secret when you do this multiplication. That it's easy to go forward, but it's very difficult to go backwards. It's like a one-way thing. So those are all of our assumptions. Let's get into let's start to talk about like our trusted setup. So a minute ago, we said, all right, we want to evaluate this at this secret point. And that's fine, that works well. But like, how can we calculate our secret point? And how can we calculate it in a way that we're able to evaluate at that point without anybody knowing what that value is? So let's do our trusted setup. So, okay, so basically a trusted setup is where we generate our secret. And this trusted setup is going to be simple. It's going to be just one person and we trust that person. In reality, when we're doing like ZKP trusted setups, we're gonna want to do like a trusted setup with more participants, and we can do that easily. We just, instead of having one person contribute a secret, we can have many people contribute a secret, and there's ways to do like multi-party computation in order to do this. So that should be fine. Right. So basically, we start here with our X value. Yeah. Okay. So basically, what we want to do is we have our polynomial here, and we want to calculate all the powers of X that go into our polynomial, right? So basically we have X squared, X cubed, X to the N. We want to calculate all of those. So what we do is we first of all, we encrypt our secret, right? I wish I could highlight. Anyway, first of all, we encrypt our secret. Is this full screen? Yeah, this is full screen, right? Anyway, yeah. Okay. Yep. So okay, cool. Thank you. All right. So first of all, we encrypt our secret. So we take G1 and we multiply it by secret, and basically our secret is now encrypted. We can't find our secret anymore. At least from the result of this computation, we're not able to go back and extract the secret out of it. So we encrypt our secret here, then we square our secret and we encrypt it again, and then we cube our secret and we encrypt it again, and we just basically do this as many times as we want. And each time we just raise our secret to the next power and we encrypt that again. And this is what we're going to call our proving key. So our proving key is basically like these increasing powers of the secret point that we're gonna be evaluating, and that's all that the proving key is. And the verification key is like much simpler. It's just in a different group, we encrypt secret in a different way, basically, right? So we encrypt our secret in G2, so that we're not able to compare these two directly. But we are able to see, we are able to say that, okay, we have one thing in G1, we have one thing in G2, and we can compare them with a pairing, but there's no way to like directly compare them, right? We're able to use our pairing to convert them both to the same format, but there's no way to directly compare them. So, okay, let's take let's go take an example, right? So we want to do a trusted setup. We start, we have like G1 times secret to the power of 1, and we have G1 times secret to the power of 2, and you get it. It's all still kind of like simple stuff. We're just multiplying a generator by like a secret number and to different powers. Easy. And we end up with a list of these numbers. So let's have a look. and say that, okay, let's actually calculate it out. So in the first case, our secret is 2. So let's say our secret is 2. So then our proving key, the first element, is going to be 2 multiplied by G1. In the second case, our proving key is going to be 2 squared, 4 multiplied by G1. And in the third case, it's going to be 2 cubed, which I think is 16, multiplied by G1. And that's our proving key. We just did our trusted setup. Great job. And then we can do the same thing for a verification key. It's just 2 multiplied by G2. Easy. The important thing to remember here is that like this is actually evaluated, and this turns out to be like a field or like a elliptic curve points. And it's not easy for us to calculate the secret based upon the actual calculation. I didn't do it here, but we can do that relatively easily. Yeah, we just have to add the elliptic curve piece, but I didn't want to do it just to keep it simple. Yeah, sorry.
Oh, sorry, real quick. Also, could we get a link to the slides as well that I can drop into Discord?
Yeah, can I give that to you at the, maybe that's on my clipboard.
I think it's, well, you're in browser, right? So the URL should be accessible.
Oh, yeah, is that, okay, I thought that was a share link. Okay, here you go.
I think that should work. Let me see.
Okay, I send it to you on Signal there. Cool. Okay.
I have a question about these generators. The elliptic curve is a group, and a group can have multiple generators. So, but you define the operation to be multiplication, but the generation, you said it's sum. You should
Right.
I was asking if it's not the same in the taking the elevating the power. Did you want the power of the secret? Or I'm confused.
Right. So I think that doing the multiplication is the same as doing like a bulge of additions.
But what does addition mean in this field? Is the field operation?
Right. So it's not in the field. It's on the elliptic curve. Like in an elliptic curve, we can define special rules to do like a point addition. So you're basically taking 2 points and adding them together.
Okay, like, so the group operation of the elliptic curve.
Yeah.
Okay, thanks.
Cool. Yeah. So we can define this group operation that does addition, but we can also define this group operation that does multiplication. Cool. Yeah, and that's what we're using here. We're using this like group multiplication operation. Cool. Okay, so we do this is our example setup here. Cool.
Oh, quick question. Yeah. How are generator points usually chosen?
Yeah, I'm not sure. I think they're just chosen randomly. I think they just kind of like you kind of just have some randomness, you hash it, you convert the hash to a point in the field, and then you convert the field to so you convert the hash to a field element, and then you evaluate the elliptic curve at that field element. You get a point, and then you just check if it's a generator or not. I think there's some easier way to check if it's a generator or not, instead of just checking every single point, which would take forever. I think there's like an easier way to do it. So generators normally random points.
Thank you.
Cool. Right. Okay. So we did our setup. Now let's evaluate our polynomial at the secret point. And right. So we're taking our secret as equaling 2, and we're saying, okay, we're going to evaluate the polynomial at this point. So when you evaluate a polynomial, what do we need to have? Well, we need to have x cubed, x squared, and we also need to have the coefficients of the polynomial. And once we have both of these things, then we have enough to like evaluate our polynomial. So we can sort of easily evaluate our polynomial by just saying, okay, 2 cubed is 8, and 2 squared is 4 times 2 is 8 plus 5, it's 21. So when we evaluate our polynomial at point 2 is 21. but when we evaluate it using our like G1, G2 secret, it will actually be like 21G, right? Right, because every time instead of instead of replacing X with 2, we replace X with the like 2G1, 2G, we replace X with 2G1, we replace X squared with 4G1, we replace X cubed with 16G1. So we end up with like, there's like the actual evaluation, and then there's this like kind of encrypted evaluation where we don't know what the actual value is, but we do know, oh, it's a point on the elliptic curve. Cool. So, okay, so now we're getting to the hardest point. I think that like we're already at the point where like this is kind of tricky. It might take a little bit more concentration for the next slide or two, but as soon as we get past that point, it's easy stuff again. So, right, so now we want to evaluate this polynomial. So we already evaluated this polynomial at a secret, and we got this kind of like commitment to it as like a field element. And this is the evaluation in the clear. And like, let's say that, okay, so we have our evaluation in clear, and we also have our like encrypted evaluation. So given our like evaluation in the clear, we want to prove that like the evaluation at X equals 6 is 293. And we want to prove this. And basically what we can say is we can prove it by saying, okay, so we know the evaluation at a single point, X. And if we subtract and basically we do this like subtract and divide trick, where we basically say that like our polynomial minus the evaluation at the other point divided by, yeah, so it's our polynomial minus the like result of the evaluation divided by the point of the evaluation equals this like quotient leftover points. So basically we're proving that X minus 6 is a root of the polynomial Px minus 293. Cool. So yeah, so basically we have to calculate Q, and Q is basically the quotient. It's just we kind of take this, this is not right. This should be Px minus 293 divided by X minus 6. But anyway, so this is how we do it if we know the secret, that we're able to just plug the numbers in and kind of calculate it out. And we can see that like, okay, so this is going to be 21 minus this, and then this is, yeah, we can basically plug it in and calculate Q, and we can find out, we can make this check that lets us prove that, oh, we open this polynomial at this point. So that's how we do it in the clear. And then, okay, let's talk about doing it in the kind of encrypted form where we don't know the secret, or the secret's not kind of in the clear. So basically what we do is we do our setup, we evaluate our point, our elliptic curve at the secret point, and then we do our subtract and divide trick again. And basically we say, oh, because I know, basically we say, yeah, so we do the subtract and divide, but we don't do the actual final check. This is kind of like all of the inputs to our check. And it's not possible for us to check this equation here if we don't know the secret. So basically what we need to do is like, if the secret is unknown, how are we able to compare? How are we able to check this evaluation? How are we able to compare this polynomial with like this much smaller polynomial here? So still, this is the super hard part. We're almost finished with the tricky bit, but we need to pay attention for like 1 or 2 more slides. So if the secret is unknown, yeah, if we don't know X, how can we calculate X minus Z, right? Because like part of this is that we have to be able to calculate X minus Z, but if we don't know X, how can we do it? Well, the answer is that we can use the verification key, the other part of our trusted setup. So if we run back up here, we see that our verification key is G2 times secret, right? So we did something in G1, and now we're doing something in G2. yeah, so we did something in G1, like we calculated px in G1, and now we're calculating x minus z in G2. Yeah, so the proving key is in G1 and the verification key is in G2. And like when we do this calculation, we end up with like this, but one of the pieces is in G1 and the other piece is in G2. And it's not possible for us to compare those directly, but we need to be able to, because it's like comparing G1 and G2 is like comparing hats and oranges. It's not possible to like directly compare them. We need to convert them to the same format. So we use a bilinear map that takes like something from G1 and something from G2 and moves it to GT. And when we're in GT, we can directly compare. Cool. So a pairing, it basically does this. It's like it does a multiplication and it does like a bilinear map. It lets us bring something from G1 and something from G2 into GT. And when we get to GT, we're able to do the comparison. And that's basically what we do. We start out with our like polynomial in G1, which is like px, which we calculated at the start. And we subtract away from it a, which is the value that we want to prove x minus 6 evaluates to. And when we do that, we know that it's when we subtract a from px, we know that x minus 6 is going to be a root of that. And basically what we're saying here is that q multiplied by x minus 6 equals this thing. So we're proving that it's a root, because if it's not evenly divisible, then the polynomial here is going to be it's going to be huge. It's not going to be possible to represent it because it's going to be like a partial. It's going to be, so basically we're proving that it's an even division, that there's no remainder. If there's a remainder, our polynomial here will basically be infinite. Right, so basically, so that's what we do. We have our left-hand side is in G1, our right-hand side is in G2. We do our pairing to convert them both to GT. And when we do that, we can do an equality check to compare the two. So that's the hard part. This is the tricky part that is like the most difficult piece of the presentation to kind of understand. So we did it. We got here. I'm not sure how clearly I described this, but any questions up until now?
For the audience, I'll also note that we're going to have a session tomorrow on polynomial commitments in a little bit more depth with Yi-san. So if this went a little fast, then don't worry, because tomorrow we'll go into more depth.
Okay, cool. That's great. Yeah, cool. Okay, cool. Let me jump into the next part of like, okay, so like we finished doing the polynomial commitment part. We finished the hard part. We did our setup, we did our polynomial commitment, and we did our pairing. And with all of those things, we're able to do an opening. We can use this to build constraints, and we can use this to check public inputs. We can use this to do a whole bunch of things as well. So next, right. So now what? We have our polynomial commitment. Let's try and make something with it. So like, let's do something really simple. Let's try and just check a bunch of multiplications. So let's take our inputs AI, A, B, and C, and let's say, okay, AI times BI has to equal CI. And this is a sample problem. It's 1 times 1 equals 1, 2 times 2 equals 4, 3 times 3 equals 9, 16, 4 times 4 equals 16. Cool. So basically we can use openings to build a simple constraint, right? And sorry. Cool. Yeah, so we can use openings to build a simple constraint. So let's say that we want to make sure that A times B equals C. So what we say is we let our prover commit to AX, BX, and CX, which are just polynomials that evaluate to the correct numbers here. They evaluate to whatever the prover wants to prove about, and they commit to them. And then basically what we do is we select a random number OR, and we ask the prover to open A or B or and C or at that point, at the random point. And then after they do that, we check A or times B or minus C or equals 0. And the way that we we check this opening is correct is we use polynomial commitments. So we do this check and we kind of get this and we just can confirm that this equation is correct. So and like the reason, oh yes, so that's on the next slide. So how do we check the proof? So don't we have to check at every place on the polynomials? Like it seems that if you just check at one place, that it's easy to have hiding in another place in the polynomial a different evaluation. So how do we check to make sure that it's correct? Don't we have to check at every single place? And the answer is no, we don't have to check at every single place, because like with overwhelming probability, when we generate a random point, it won't be like one of the places where it's actually where the values evaluate to 0. It won't be a place where it evaluates to 0. It'll be like another point. And when we evaluate at that other point, we'll basically get this like rich information from the polynomial. And like, if you try and make a polynomial that's like exactly the same at every other place, but different at one, it's really, really, really hard. It just takes a lot of work to do that, because like polynomials encapsulate, like they use like very limited information to define very complex data structures. And if you change like one of the points, it will have like huge impacts for the rest of the points, for the rest of the polynomial. So basically polynomials act as this kind of like error amplification, where if you change it at one, it kind of changes everything. Right, so cool. Yeah, so basically checking at a single random place is the same as checking at like every place on the polynomial. Cool, so let's do something a little bit more complicated. Let's do some, so that's multiplication. We're able to check A times B equals C, and that's basically how we do a multiplication check. So let's do something a little bit more complicated. Let's do like the square root formula. So let's kind of like, given A, B, and C, calculate, given columns A, B, and C, calculate the square, the roots of that. Sorry, that should be roots. Calculate the roots of that, the polynomial represented by that A, B, and C. So we can also do that too. We just have to change our verification equation a bit. And we change our verification equation like this, so that we say that like, we have to add an extra column. We have A, B, and C, but we also have root. So we add an extra column, and then we also increase the size of our verification equation. So this makes the verifier more complicated, because like, first of all, we add an extra column. That means it's another polynomial opening. And secondly, we have A, B, and C, but that's the same as before. But secondly, we have just like more arithmetic to do in our verifier. We're still checking only one point, as we are here, but it includes like more arithmetic. It includes like 2 squares and like a couple of other things. So there's like more complexity in our verifier here. And like when we do something like this, where we kind of specialize our verifier in order to be able to evaluate the polynomial, in order to be able to like do more complicated stuff, this is called like a custom constraint. And like there's like one of the big optimizations that we're able to use with PLONK is that we're able to make these custom constraints relatively easily. And like we can make them, but we can also have like more complicated circuits that have like multiple different custom constraints, and you can turn off one, you can turn on another. And here is basically how we can go about doing that. So that's how we do our proof stuff. So we're able to have proofs about multiplications. We're able to have proofs about like basically anything that we can represent with arithmetic. It does increase our verifier cost, and it also increases our prover cost in some cases. Yeah. But one thing to remember is that like, although we're checking like this single relationship between like A, B, and C, like 1, 1, and 1, 2, 2, and 4, 3, 3, and 9. Although we're checking this single relationship, we're not checking that like things are happening between like different rows in our table. And this is important because a lot of the circuits we're going to make are going to rely upon copy constraints. And copy constraints we can also talk about, but we didn't really go into that here. Cool. Okay, so that's how we do. That's a brief introduction to how we do like elliptic. That's a brief introduction to how we do like make proofs. And now we can talk about, yeah, that's a brief introduction to how we make proofs. And now we can talk about like ways that we can make our prover more efficient. So how does our prover work? So basically our prover, the main work that we need to do in this like super simplified scheme is to make polynomial commitments and evaluate them. So we need to calculate, so given A, B, and C, we need to calculate the polynomials AX, BX, and OR of X, and that should be C of X. Oh, that should be C of X. And like in order to do this, we can use an inverse FFT, which we'll talk a little bit about in a minute. And we have to do this 3 times. And then we also need to build a commitment for, wait, yeah, we need to calculate the polynomials, and then we need to what is that about? Okay, so we need to build the polynomials, and then we need to calculate the openings of the polynomials. When we calculate the openings of the polynomials, we need to calculate Q. And Q is basically like a division of A of X divided by the random X minus the random point that you're evaluating it at. Okay, cool. So that's our simple prover, how our simple prover works. So let's talk a little bit about like the forms that you can represent your polynomials in. Like the first form that you can represent it in is like coefficient form, where you have like A plus B times X plus C times X squared plus D times X cubed. That's like coefficient form. And like when you're in coefficient form, addition is really easy. Like you can add two polynomials together really, really simply, because you just take like each of the ascending powers of X and you just add them together. So addition is really easy. But there's another way to represent polynomials where multiplication is really easy. And like the way that we do that is that like if you evaluate your polynomial at a whole bunch of different points, you can convert your polynomial from coefficient form into evaluation form. And when you're in evaluation form, multiplication becomes super easy. I think that like multiplication is you just do like a pairwise, you do a pairwise multiplication. So for each point that you evaluated at, you just multiply it by the other. And that's how you do, is it multiplication or is it addition? I'm not sure, but it's super simple. It's just like a single operation for each. So like if we're able to convert from coefficient form to evaluation form, that's really helpful for us. And like, so there is an algorithm that lets us do this. It's called fast Fourier transform, FFT, and to go backwards, it's inverse fast Fourier transform. And like, okay, so let me just give an intuition about how FFT works. So basically there's these kind of like, when you're dealing with prime fields, there's these kind of magic numbers. There's these magic numbers that form this like repeated pattern every time you square them. So let's take like prime field 7, and let's take the number 2. So if you take 2 and you square it, you get 4. If you take 4 and square it, you get 2 modulo 7, you get 2, and like you just keep going around and around and around. And like you stay, and like because we're doing this, if we have a polynomial that we want to evaluate at X equals 2, it's super easy because we just have to do 2 squares. We just square something twice, and then the rest of it is just additions. So because this is repeating, we can save lots of work when we're doing our evaluations. We don't have to do the squares. We can just automatically calculate this this kind of evaluations of the ascending powers of X modulo 7. So, and this is a super efficient way for us to convert from evaluation form to coefficient form, and we end up using FFTs a whole bunch because we need to do a bunch of multiplications to calculate Q, and we need to do it for some other arithmetic that we need to do for copy constraints and things like that. Cool. Okay, so let me that's basically the end of all of the kind of like arithmetic stuff, or like the kind of math part of things. Let's talk about like the lookup argument. So like previously we talked about custom constraints, which is like an arithmetic way of defining. It's an arithmetic way of defining constraints. And like the limitation of custom constraints is that you need to define things. You need to define things with arithmetic, and that can be really difficult. And like instead, it would be good. Instead, it would be good. Instead, it would be good if we can evaluate things as. Sorry, I lost my train of thought. Just 1 second. Instead, it would be good if we can describe things as like truth tables. That seems like a much simpler thing that would help us to describe circuits a lot easier and a lot more expressively. Because calculating like a 2-degree polynomial that expresses the truth table of an AND gate, it's really hard. But it's not. I'm not sure if it's actually really hard or not. But like it's annoying and it's complicated. And even if you can do it with an AND gate, you can't do it with like more complicated logic that we're going to want to be able to encapsulate. And one example of this that I think someone mentioned in the kind of introductory part is like doing range checks. That like basically you want to do a range check to see if a number is bigger than 2 to the 16 or whatever. You want to say it's less than this, and when it's less than this, you can do some big integer arithmetic. You know that the arithmetic you do is not going to overflow, and then you're able to like continue with the arithmetic. And this is an example of some stuff that comes up with the Circum ECDSA, I'm sure. So range get checks can help there. We can also do like multivariant lookups where you're able to look up like, instead of having like X and Y and the results, you can have like X, Y, Z, P, Q, and then the results. You can have like this multi-dimensional table that you're able to look up, which can also be super useful when you're trying to build things. Cool. So that's like, those are the two superpowers of PLONK, custom constraints and lookup tables. And like these can technically be applied to Grot16 too, but it's just a lot more work, I think, to be able to include it there. But it might be interesting to explore that because I haven't really investigated. But anyway, Ultra PLONK lets us do like Ketchak, it lets us do ECDSA, and I think it would let us do that a little bit more efficiently than we currently can do it with Grot16 and with Circum. And this is for sure something I'd be interested to explore. I actually should have put some numbers here, but I didn't have time to do that. The other thing that like is really interesting for us to do is this idea of recursion. And like recursion is basically where you have one ZKP that verifies another one inside it. And this is really helpful for a whole bunch of things. And it helps us build a bunch of new applications. It also helps us make like better applications. Like for example, like making proofs on mobile is really difficult, especially for bigger circuits. So like one thing that we can do is we can have like this really cheap mobile prover that basically gives like zero knowledge, but it doesn't give any kind of like data compression. It's like the proofs are huge. And then we can have another round of computation that happens on some server that compresses this big proof into like a much smaller proof. So this is one thing that's super interesting to explore. The other thing is proofs of consensus, and like the idea here is that like right now we just make proofs about like ourselves, that like I have money on Tornado Cash, I know the coordinates of a forest on dark planet of a planet on dark forest, but like we want to be able to make proofs about like a much broader set of people. Like I want to be able to make a proof about like other people and like my connection to them. And in order to do that, I need to either have their private information, or we need to have some kind of recursion so that they can give me a proof that I can make a proof about. So like one example of this is like eigentrust, and another is like proof of satisfiability. But let me just skip those because I'm getting close to the time and I want to have some time for questions. So future work is like, can we make better polynomial commitment schemes? can we make it less work to open them? Can we pre-compute openings? There's another talk here about like polynomial commitments. That's like 3 parts long, and it goes into like a lot of detail about like different schemes. Yeah, another thing that I think would be super exciting to do is to compare like some of our implementation of like Ketchak and ECDSA with the Circum implementations, do some benchmarks and like compare the prover costs and things like that. I think that like at the moment our prover is still a little bit inefficient, so it might not be. Yeah, I think that this is like a key metric that will let us know when it's time to move from Grot16 to some other kind of proof system. Okay, cool. So that's the end of my talk. Thank you for listening. Is there any questions?
Thanks, Barry, for the overview. I had a quick question in terms of, I guess, practical projects. Have you seen any characteristics where of the projects where they have tried PLONK more than Grot16? Is it mostly just because of the trusted setup, or do you think there are other kind of broad characteristics that make PLONK superior in those cases?
Yeah, so I think that like there's like most of the ZK EVM projects use either. I think that like the one that we're working on uses UltraPlonk, and it uses it because UltraPlonk provides us with lookup tables, which is super important for like being able to do like big integer arithmetic and things like that. But it's also super important for being able to do like programmatic switching, to kind of switch between like, oh, I'm doing the state and now I'm doing the EVM execution, and like having proofs be able to talk to each other in like an efficient way. Like all of those have led us to build with UltraPlonk, because it provides like more programmability, and also it's not as expensive to make things like Ketchak and ECDSA. Things like this need to be super efficient for zk-AVM stuff. So we decided to build with UltraPlonk to just try and like reduce our program complexity as much as we could. So I think that like in the short term, people will adopt because there's no trusted setup, but I think that's rare. I think in the longer term, people will move because the programmability is a lot nicer. But I think the real killer feature that people will move for is recursion. I think recursion just unlocks a whole bunch of different like language paradigms and prover architectures and a whole bunch of different things. I think recursion is like the killer feature of UltraPlonk.
Got it. Oh, super helpful.
Hey Barry, I have a question. So besides Halo 2, are you aware of any usable tool stacks for UltraPlonk? I know that Circom supports Plonk, but not custom gates or VLOOKUP. And they have like a work in progress PIL language. Are you aware of any others?
Yeah, so I think that 0x Garage people are working on some stuff. I think that there's some basic tools in the Dusk Plonk repo. I would also check on. Ooh, I can't remember the name. What is that called? No, I can't remember the name of the last one, but I don't think that they use it, because I think they do recursion in the way we're using different elliptic curves, like pairing cycles. So I don't think they'll have that feature. But yeah, those are the ones that come to mind. It's still very early. I think there is room for more people working on like experimental UltraPlonk tooling.
Cool, makes
and we'll
sense.
for sure support. Yeah. Cool. Yeah, one thing I wanted to mention, I wanted to touch on some of the projects that you all mentioned at the start. I think, Jason, the idea that you talked about having like some information that you don't know about yourself, that you don't know, like we have explored some of this with Macy, which is this kind of like bribery resistance mechanism. And basically it has like this kind of coordinator that knows the information about everybody, but like the individual people don't know. And like the reason we want them not to know is because we don't want them to be able to prove to other people. So there might be some interesting things to explore there. Tony, maybe we can contact a little bit about benchmarking some of the Halo 2 gadgets that we've made for ZK EVM and compare that with the like Circum ECDSA and things like that. Might be interesting collaboration there.
Yeah, definitely. I think some of my teammates you might have talked to is he's been playing around with trying to use PLONK for some of the ECDSA stuff too.
Oh, nice. Oh, cool. I'd be interested to see how that goes. Yeah, we have an implementation of ECDSA. Happy to share and compare. I think in general there's room for a project to like benchmark all of the best ultra PLONK implementations and the best Circum implementations, because that will give us a point of like when we get to the point where Circum, when like ultra PLONK is ready, and like when it starts to outcompete, it's the point where people will, I think, start to think about changing.
Yeah, that makes sense. Yeah, very cool.
Cool.
Awesome. I know we're at the hour, so Barry, if you got to hop off now, thanks for joining us. And where should people go if they have questions for you about PLONK or any of these other related topics that were brought up?
I am not sure.
I can forward
you...
questions, I guess.
Yeah, cool. I think, or tag me in the Discord.
Oh yeah,
0x Park one. But
yeah, I
I'm
can do that.
I'm very bad at Discord.
Cool.
But
no
yeah,
worries.
Brian, if there's anything I'm missing, just let me know. I'll try and get
For
to
sure.
it.
Yeah, maybe I'll make 2 notes for Jason and Lucas that yeah, Jason, regarding the like schemes to make it so that your own balance is hidden like from yourself as well. I do recall, I think the privacy and scaling exploration team had some experiments in that direction. I don't know exactly where they ended up. And then Lucas, in terms of ZK voting systems, you should take a look at Macy, and Wejia and Barry are going to have a lot of expertise on how that stuff works. So
Cool. I'm gonna jump, folks. Thanks for the call.
all right.
Happy to
Thanks,
chat.
Barry. See y'all tomorrow.
Thank you.
Take care.
Thanks, Barry.